Welcome, colleagues, to this academic masterclass explainer. As researchers and clinicians, you are routinely faced with a very practical challenge, selecting the absolute optimal intervention for your patients from a massive sea of options. But what happens when head-to-head randomized controlled trials simply do not exist between competing treatments? It happens all the time, right? Well, this is exactly where our methodology must evolve beyond the basics.
Hello, researchers. Thank you for your hard work today organizing medical meta-analysis data and creating forest plots. Today, we will delve deeply into network meta-analysis, a more advanced analytical tool within meta-analysis. Hola, investigadores. Gracias por su arduo trabajo hoy organizando datos de metaanálisis médicos y creando diagramas de bosque. Hoy profundizaremos en el metaanálisis en red, una herramienta analítica más avanzada dentro del metaanálisis.
Okay, let's just briefly look at our roadmap for this explainer. We're going to cover NMA fundamentals, planning and assumptions, models and software, results and visuals, open loops and grade, and finally, the PRISMA-NMA standards.
Section 1. NMA Fundamentals, Beyond Pairwise Comparisons.
To really grasp why we need this, we have to start with the fundamental limitation of standard pairwise meta-analyses. Pairwise analysis is fantastic, but it's inherently restricted to direct evidence. If you have drug A and drug C, and they have literally never been tested in the same trial against each other, a standard pairwise approach leaves you clinically blind. Network meta-analysis, or NMA, is the solution. It's a technique that lets us evaluate 3 or more interventions simultaneously within a single cohesive analysis. Now, within NMA, we have 2 distinct concepts. First, there's the indirect treatment comparison, or ITC. This is where we infer the relationship between 2 treatments solely through a common comparator. Think of it like this. If A beats B and B beats C, we indirectly estimate how A compares to C. But the real magic happens with a mixed treatment comparison, or MTC. This is the absolute gold standard of NMA. An MTC simultaneously mathematically combines both direct head-to-head evidence and indirect evidence. Because we're doing this all at once, we can generate a definitive relative ranking for every single intervention in your network. It's incredibly powerful.
When you set up an NMA, you'll generate a network diagram. And what's brilliant about this is how the geometry instantly communicates the strength of your evidence base. When you look at one of these graphs, the size of a node intuitively represents the total sample size for that specific treatment. Meanwhile, the thickness of the lines, the edges connecting the nodes, tells you the volume of studies making that direct comparison. Visually, you can immediately spot a massive difference between a closed-loop network and an open-loop network. A closed-loop network forms complete triangles or polygons, meaning you have both direct and indirect paths. This is what you want, because it allows you to run robust mathematical checks for consistency. An open-loop network, on the other hand, is a series of unclosed paths. It relies entirely on vulnerable indirect evidence for certain comparisons, and structurally, you just cannot statistically verify its consistency.
Moving on to Section 2, Planning and Assumptions, Structuring the Evidence Network.
You absolutely cannot treat an NMA as a retrospective fishing expedition. It requires rigorous prospective planning. This means registering your protocol in places like Prospero beforehand and strictly adhering to PRISMA-NMA guidelines. Before you even think about touching statistical software, you have to lock in your PICO framework. Crucially, you need to understand the difference between your decision set and your supplementary set. Your decision set contains the actual clinically viable interventions that doctors are going to choose between today. But your supplementary set might include something like an outdated historical placebo. Why include it? Because it acts as a bridge. It anchors the network and strengthens the indirect paths, creating your final synthesis set. Also, you have to make hard choices about node clustering. Are you going to group interventions broadly by drug class, or are you going to split them down into specific dosages? How you decide to lump or split these nodes directly dictates the validity of your entire study's baseline assumptions.
And speaking of assumptions, every single NMA rests upon 3 non-negotiable pillars: transitivity, homogeneity, and consistency. If you don't have these, your analysis falls apart. Homogeneity evaluates the comparability within your direct pairwise studies, and we usually measure this quantitatively with an I-squared statistic. Consistency demands that your direct evidence and your indirect evidence are actually pointing to the same mathematical truth. We evaluate this using local approaches, like node splitting or the Busher method, along with global inconsistency models. If there is unexplained, significant inconsistency, running an NMA is frankly inappropriate. But the most critical pillar, the foundation of it all, is transitivity.
Listen closely here, because this is where many analyses fail. Transitivity, sometimes called similarity, is the assumption that effect modifiers are evenly distributed across all your comparisons. It means there's an equal probability that any patient in your entire network could have theoretically received any of the included interventions. The terrifying thing about transitivity is that it cannot be mathematically proven. Algorithms can't save you here. It relies entirely on your rigorous, qualitative review of the clinical and methodological traits of the studies. If trial A versus B only enrolled healthy 20-year-olds, and trial B versus C only enrolled 80-year-olds with severe comorbidities, your effect modifiers are not evenly distributed. That is intransitivity. If you go ahead and run a quantitative synthesis anyway, your results aren't just flawed, they are completely inappropriate.
Section 3. Models and Software. Executing the Analysis. Assuming your network geometry is solid and transitivity holds true, it's time to actually execute the math. First, you have to choose between fixed effect and random effects models. In the complex world of NMA, random effects models are overwhelmingly the default choice. Why? Because a fixed effect model assumes one single true effect size shared perfectly across all studies, ignoring variance. That's rarely reality. Random effects models acknowledge that there's a distribution of true effect sizes and incorporate between study heterogeneity. Now, quick nuance for the advanced crowd, standard random effects NMA typically assumes a single universal heterogeneity variance across the entire network. But highly sophisticated models can actually allow for comparison-specific variance structures. You have to be particularly careful here when handling multi-arm trials, where the variances within a single study are highly correlated and require specific mathematical adjustments.
So, what software are we using to run these models? You're basically choosing between the Frequentist and Bayesian statistical paradigms. If you go the Frequentist route, you're likely going to use the netmeta package in R. It's fantastic, but it requires meticulous data prep. You use pairwise functions, and you have to explicitly define inputs like SOM for your specific effect measure and ref to set your baseline reference treatment. On the other hand, we have the Bayesian approach, typically using packages like gemtc. This leverages Markov chain Monte Carlo simulations. The Bayesian framework is incredibly flexible. Its major advantage is that it generates incredibly robust probabilistic outputs and direct treatment rankings, which brings us perfectly to how we actually interpret these results.
Section 4, Results and Visuals. Interpreting the outputs. The software is going to spit out a really dense array of visual tools. Of course, you have your network diagrams and your traditional forest plots, but you're also going to get a league table. This is a massive matrix detailing the relative effects of every single possible pairwise comparison. As you add more treatments to your network, the permutations in this table grow exponentially. You'll also use rankograms to visualize the probability of where each treatment places, and comparison-adjusted funnel plots to check for publication bias and small study effects. I also want to highlight the net split function. This is a brilliant visual tool that actually splits your network apart, separating the direct evidence from the indirect evidence, so you can explicitly and visually test for consistency.
Now, this slide brilliantly illustrates a concept that catches so many people off guard: SUCRA. SUCRA stands for the surface under the cumulative ranking curve. It's a Bayesian metric expressed as a percentage from 0 to 100, showing the likelihood that a treatment is among the top ranks. If you're doing a frequentist analysis, your analog to this is the p-score, which gets calculated without resampling techniques. But here is the absolutely vital clinical warning. A high SUCRA score or p-score does not guarantee a clinically significant effect. You could have a drug with a SUCRA of 98%, making it number one, but when you look at the actual data, it might only improve symptoms by a tiny, statistically insignificant fraction compared to the second-place drug. You must, absolutely must, interpret SUCRA strictly alongside the absolute relative effect estimates. Don't just blindly trust the ranking.
Section 5. Open loops and grade. Navigating unverifiable networks. We really need to address the elephant in the room. What happens when your clinical question forces you into an open-loop network? Remember, in an open loop, consistency is mathematically unverifiable. You have no closed triangles. Therefore, the entire validity of your analysis rests solely on that unproven transitivity assumption we talked about earlier. The danger here is very real. A recent systematic review looked at 113 published open-loop network meta-analyses. The findings were staggering. Out of those 113 studies, 96 of them just went ahead and integrated the data under the assumption of consistency without doing any advanced statistical work to evaluate or adjust for confounding clinical variables. They essentially just crossed their fingers and hoped their patient populations match perfectly. That is not rigorous science.
So how do we fix this? How do we salvage an open-loop network? It's a structured process. Step 1, you have to meticulously identify baseline risks. Systematically review your populations to see if baseline severity differs across your trials. Step 2, if you find differences, you must apply covariate-adjustment. We do this using meta-regression to account for that clinical heterogeneity. And step 3, for the truly advanced networks, is adjustment through imputation. This is fascinating. You actually simulate hypothetical, highly conservative direct evidence, mathematically inject it into your open loop to close it, and then stress test the model. If your network's conclusions don't completely collapse under that stress, you know your findings are actually robust.
Let's look at a real-world case study to see this in action. Evaluating renal protection after cardiac surgery. The researchers built a massive Bayesian NMA comparing 13 different anesthetic drugs. They were using SUCRA to determine the rankings, but the initial relative effects were a complete mess, ambiguous and overlapping. But they noticed something. They realized the baseline risks of the patients varied wildly across the decades of literature they included, so they implemented meta-regression. By adjusting for those baseline covariants, they successfully stripped away the heterogeneity. Suddenly, the noise cleared, the treatment effects separated out beautifully, and they were able to provide a highly reliable ranking of those 13 drugs for clinical practice. It was a perfect save.
Once you have your results, you have to objectively grade the certainty of that evidence. We do this using the SNMA framework, which stands for Confidence in Network Meta-Analysis. It's essentially a brilliant web application that expands the traditional grade approach specifically for the complexities of NMA. SNMA evaluates every pairwise comparison across 6 specific domains: within study bias, reporting bias, indirectness, imprecision, heterogeneity, and incoherence, which is just another word for inconsistency. I really want you to pay attention to domain number 4, imprecision. When you're working with sparse networks, automated algorithms will often trigger a spurious downgrade for imprecision just because the direct data is thin. But as the expert in the loop, you must review this. If your indirect evidence is overwhelmingly strong and mathematically sound, you should intervene and prevent that automatic downgrade.
Finally, Section 6, PRISMA-NMA Standards, Publishing with Rigor.
At the end of the day, no matter how beautiful your math is, you have to report it transparently if you want to get published in a high-impact journal. The PRISMA extension for netmeta is your checklist. Pay close attention to items S1 and S2. You can't just write, "We ran the software." Under S1, you must explicitly describe your network geometry and justify your rationale for how you clustered your nodes. Under S2, you have to detail the exact methods you use to evaluate both global and local inconsistency. When reporting results, you must report your SUCRA rankings right alongside your absolute summary measures, never in isolation. If you ran a Bayesian analysis, you are required to mathematically justify the prior distributions you selected, and of course, you must unambiguously report all funding and conflicts of interest. This transparency is the only way we maintain clinical trust.
Which leads us to a final critical thought I want to leave you with today. As you head back to your labs and your clinics, consider this. If you come across a published network meta-analysis that relies almost entirely on unverified transitivity through indirect pathways, and the authors failed to perform rigorous covariate adjustment or meta-regression, can we truly trust the clinical guidelines that paper produces? I'd argue we can't. The software will always give you a pretty chart and an output, but it's your rigorous methodological scrutiny that actually finds the truth. Thank you so much for joining me in this explainer today. It's been an absolute pleasure.